Coming to the inverters. So what are the inverters? Inverters will convert DC input to the AC output. So AC doesn't mean only sinusoidal. It can be square or anything whose DC content is 0. Right. Okay. So here in the first case we will see single phase half bridge inverter. So here we use, as it is half bridge, we use only two thyristors and there will be two diodes in anti-parallel with them. So as I said, input is DC and the load is connected as shown in the figure, and here the switches, that is thyristors, has to be switched such that we'll get AC output. Okay, so when T1 is turned on, the output voltage across the load will be plus Vs by 2, and when T2 is turned on it will be minus Vs by 2. So in that way we should turn on and turn off those two switches so that we will get the output as shown in the figure. So this is very simple inverter. Okay, then coming to the single phase full bridge inverter. Here, as it is full bridge, it is of bridge configuration with the four devices or four thyristors. Similarly, anti-parallel diodes will be there, and so the input is Vs DC, and here also the switches should be turned on and turned off so that we will get AC output. So when T1 and T2 are turned on, the output voltage will be plus Vs, and when T3 and T4 are turned on, it will be minus Vs, so that it will be symmetric and the DC content will be 0. But if you observe, they are not pure sinusoidal, they are of square waveform. So we will see what we are going to do with these waveforms. Okay, got the output waveform as a square waveform, right? So then generally the load consists of RLC. So okay, and so if the load is R, only R, the output current will be just in phase with the voltage, because R load is unity power factor, there is no phase difference. Okay, then coming to the RL load, the current should lag the AC input voltage. Means for load the input voltage is the output voltage, like okay, leave it. So the voltage across the load RL load is V0, and so the current through the RL load should lag that V0. Okay, so as I have shown there, so when that is lagging during the negative half period in the first half of the input cycle, D1 and D2 will conduct, and in the same first half there will be some portion which is positive in case of current. That means T1 T2 are going to conduct. Similarly in the second half there will be two cases, positive and negative currents. So accordingly the devices will conduct. Okay, coming to the RLC load, this is very important. Okay, in case of RLC load there are two cases, overdamped and underdamped. So here if you see, the current is of sinusoidal waveform. This you will get if you solve the system using Laplace transforms or anything. Like if you have RLC, it is second order, right? So you will get denominator s square plus and all. So s square means if you do inverse Laplace you will get sinusoidal or cosine, whatever it is sine only. So that's how you will get these responses. Okay, right? So RLC overdamped. Overdamped means based upon the values of RLC, you can have a second order system with a response of either overdamped, underdamped or critically damped. Okay, so if it is overdamped, this is the situation. So in the first 180 degrees, initially D1 D2 will conduct, then T1 T2. Okay, but If it is RLC underdamped, the waveform will be as shown, like in the second case. So during the first 180 degrees, in the first phase T1 T2 will conduct, then D1 D2 will conduct. Okay, means underdamped means load current leads load voltage. But if you observe in case of overdamped, the load current is lagging input voltage. That means inductive nature is more in case of overdamped, whereas in case of underdamped, capacitive nature is more. That means capacitance C is more. That's what it is. Okay, so this is very important actually, RLC case, because there are two different cases, overdamped and underdamped. So now in some questions they will ask you find out the value of C in order to obtain load commutation. So what is meant by load commutation? So this will happen in case of RLC underdamped. That means there is some time, there is some commutation time that is going to be applied due to the presence of the some values of RLC. So those values going to lead to underdamped response. In case of overdamped, it is not going to happen. Okay, but in case of in case of overdamped, it is not going to happen. In case of underdamped, load commutation is going to happen. And let us say some values like resistance 2 ohms, omega L equal to 10 ohm, and periodic time is 0.1 milliseconds, let us say. So, and it is given that thyristor turn off time is 10 microseconds. And what is TC? Circuit turn off time. Okay, thyristor turn off time is different, circuit turn off time is different. And you know, circuit turn off time should be greater than thyristor turn off time. Okay, that is equal to 1.5 TQ. And you know, tan theta, that is the phase angle relation with the capacitance, inductance and resistance, is that tan theta equal to XC minus XL by R. And you also have TC is 1.5 into TQ means 15 microseconds. So theta equal to omega T, and theta by omega will be TC, right? So that you need to use there. Okay, so omega you have, and also you have omega LR. So if you substitute all these in the tan theta formula, you will get capacitance. That's it. This is an important question actually. Okay, right. Thank you.